The purpose of today's discussion is to understand how the surge control logic is used, and it is developed based on stage differential pressure boost versus differential pressure flow in percentage data. So let's start the discussion. Uh, this is again a multi-stage compressor. Stage 1 compressor, stage 2 compressor, and stage 3 compression, and it is taking suction from either atmosphere or process gas, and it has IGB and it has anti-surge control valve. In case of air compressors, it is bending to atmosphere, but in case of process, it is returning back to suction. And then one NRV is there, non-return valve and discharge valve, and then connected to system pressure. So PT1 is inlet pressure of compression, but please note that it is a stage 2 inlet. So PT is installed here. It is not the inlet of a stage 1, but in stage 2 compression. And range of PT1 is 0 to 5 bar. PT2 is final discharge, but please note that it is a stage 2. It is not final, but it is a stage 2 discharge compression. So it is a PT2, and range of PT2 is 0 to 10 bar. PDT is a differential pressure transmitter of FT, and range of PDT which is installed at the suction of stage 2 compressor is 0 to 500 millibar. PT1, PT2, PDT and FT, PDT of FT are connected through electrical signal to PLC or DCS. In addition to these, all other instrumentation and control valves are connected to PLC and DCS. So this we'll see how we can develop using the surge control logic, DP flow versus DP stage in percentage data. Now converting PT1, PT2, PDT in engine data, differential pressure or DP boost is equal to, please note that this is not final discharge, but it is discharge of selected state. In this case is stage 2. So discharge of stage 2 minus suction of stage 2. So it is written as PT2 minus PT1. So discharge of stage 2 compressor minus suction of stage 2 compressor. So PT2 minus PT1 is a differential pressure boost. Converting engineering data into percentage, so percentage of differential pressure boost is equal to 100 into engineering data upon range of PT2, because the larger transmitter range is selected. So in this case PT2 is larger. Normally PT2 is larger than PT1. Percentage of DP flow is 100 into engineering data upon range of the PDT. So now we have data of DP flow and DP boost in percentage units. Surge line, the surge test of compressor conducted for minimum 3 IG position and maximum any number of points. DP flow and DP boost are in percentage data. It is collected during the surge test in the field. DP boost is drawn on x-axis, DP boost in percentage is drawn in x-axis, and DP flow in percentage is drawn on y-axis. Surge slope is equal to DP flow percentage upon DP boost percentage. Slope is calculated using the average surge test data, and surge slope is coming during the test. This is an example, is coming 3.5, and surge bias is 0. In this logic, always the surge bias is 0 and surge slope is 3.5 is an example. It can be any number. Now surge control line, surge slope is 3.5, bias is 0. Let's say surge safety margin on surge slope is 10%. So surge safety margin will be 3.5 into 10 by 100, which is 0.35. So surge control slope will be surge slope plus surge safety margin. So surge control bias, sorry, it is not bias, surge control slope wrongly written bias should be slope. 3.5 plus 0.35 is 3.85. But please note that surge control bias is equal to surge bias with 0. So both case surge bias is 0, but surge control line slope is larger than surge line slope. And this region is a safe operation of the machine. And this is not safe. This is unsafe zone. Operating point DP flow is 10% and DP boost is 10%, DP flow is 85%. So see, it is 10%, 85%. So this is the point of operation. So machine is operating in the safe zone. PID controller, proportional integral and derivative control, developed in PLC or DCS. Input data or process value, which is written as a PV, and set point is SP. One controller output. Output of PID control will give command to anti-surge control valve through 4 to 20 milliamperes electrical signal to position of anti-surge control valve to operate it. Process value PV is equal to operating DP flow percentage into F upon operating to boost percentage. Set point is average of surge test data of DP flow percentage upon DP boost percentage plus surge safety margin bracket close to the factor F. F can be 1 to any positive number. Typical value is 1, 10, 100, 1000, etc. Logic, PID logic is if PV is greater than SP, the anti-surge control valve will close. If PV is less than SP, anti-surge control will open. If PV is equal to SP, anti-surge control valve will be in the last position. Anti-surge control valve operation. Let us assume operating DP boost is 10%, operating DP flow is 85%, surge slope is 3.5, which is constant. Let's say 10% margin, which is as the 3.5. Sorry, surge slope is 3.5. So 10% margin, 3.5 into 10 upon 100, which is 0.35. Surge slope with margin is equal to surge slope plus safety margin. So surge slope with margin we can write 3.5 plus 0.35, 3.85 constant. Set point will be surge slope with margin into factor F. Set point will be 3.85 into 10, which is 38.5 constant. Operating slope is equal to operating DP flow percentage upon operating DP boost. So operating slope is 85 by 10, 8.5. Process value will be operating slope into F, 8.5 into 10 is 85. Now logic of PID, since PV 85 is greater than 38.5, PV is greater than 85, so anti-surge control valve will close. So if compressor operates above the surge control line, it is safe and anti-surge control valve will close. If operating below the surge control line, it is not safe and anti-surge control valve open. So this zone is a safe zone, and if machine is operating above this zone is safe. The moment it operates below this, it is not safe and machine will anti-surge control valve will open it. So thank you. With this I have finished this discussions. Hope you will like this. If it is so, please subscribe my channel, like it, share it, so that you will get the intimation of new video. See you in the next discussion. Till then, bye bye. Thank you.